Imagine a patient with off-the-charts intelligence. They read complex literature with perfect comprehension and score in the top percentile on logic tests. But when this person stares down at a table with 4 apples on it, they freeze. They could easily debate the nuances of existential philosophy with you, yet to tell you how much fruit is sitting right in front of them, they have to physically point to each apple, counting 1, 2, 3, 4. Their brain is perfectly healthy when it comes to language, reasoning, and memory. The only blind spot is numerical quantity. If math were merely a byproduct of general intelligence, this specific deficit could not exist. This clinical anomaly suggests that the brain utilizes a dedicated, specialized system for numbers that operates alongside our general intellect. We often treat mathematics like reading or writing, a cultural tool that humanity invented, something you have to sit in a classroom to learn. The reality of dyscalculia dismantles that assumption. The condition mirrors a sensory deficit, appearing as a physiological hurdle that persists regardless of a student's schooling or effort. Long before anyone opens a textbook, humans possess an innate biological intuition for numbers. It functions exactly like vision or hearing. And just like someone can be born with a visual impairment, a person can be born with a biological blind spot for quantity. Mathematics begins as a hardwired survival instinct. The symbols and equations we learn in school are simply layered on top of it. This instinct is easiest to spot in an ability called subitizing. When you see a small cluster of items, like 1, 3, or 2 dots, you don't have to count them. You instantly recognize the total, an automatic reflex bypassing your conscious brain. We aren't the only ones who have it. In the wild, primates use this rapid quantity assessment to decide whether to fight or flee from a larger group of predators. Human infants exhibit this exact same reflex when they are only a few months old, long before they've acquired a single word of language. The fundamental architecture for human math is rooted in an ancient evolutionary survival mechanism. We even know exactly where this hardware lives. It sits right here in the parietal lobe, inside a fold called the intraparietal sulcus. When we place people in MRI scanners and ask them to estimate physical quantities, this specific geography aggressively lights up. But estimating dots is a long way from solving calculus. To bridge that gap, our brain has to recruit its language centers. Those language centers act as translators. They take the raw biological feeling of quantity and convert it into the abstract symbols we recognize, like the Arabic numeral 3. What we call human mathematics is actually a collaboration between our ancient visual hardware and our newer linguistic software. This biology requires us to look at the old trope of not being a math person in an entirely different light. Falling behind in algebra or statistics is not a moral failure. It doesn't mean a student isn't trying, and it certainly isn't a sign of low intelligence. Conditions like dyscalculia or even general difficulty with numbers are simply natural variations in the physical structure of the intraparietal sulcus. By treating these biological hardware differences as purely academic shortcomings, our current educational system causes massive amounts of unnecessary frustration. We have to identify these physical roadblocks early in a child's development, rather than waiting to punish the symptoms on a standardized test. The goal of modern adaptive teaching is to find alternate routes, new ways to build a cognitive bridge between a student's internal sense of quantity and the abstract symbols on the chalkboard. Mathematics stands as one of humanity's most remarkable biological achievements. When we finally understand how our brains process numbers, we strip away the mystery of the subject and rethink the boundaries of human intelligence.